Thank you so much for having me here. I'm not used to speaking at 11 in the morning. I don't just mean like on stage, I mean like just generally. I don't really speak at 11 in the morning. Because this is a symposium on art and science, I thought I would start with a description of Pioneer Works because many people here have not heard of it. Pioneer Works is a cultural center in Red Hook. It was a complete labor of love when it began. It was completely cart before the horse. It just started with artist Dustin Yellen as the founder, and the founding artistic director, Gabriel Florence, literally put this old ironworks back together with their bare hands. And when I came in, I said I used to sit upstairs on the third floor. It was still unfinished, this building, and I would just kind of look out the window and dream of doing things like what we're doing here today. And it was as though we were building the world we wanted to live in because it didn't exist yet. It had this very strong feeling. And I came in to bring sciences in, but really there was no, people were asking me like, what's your mandate? There was no hiring process. There was no mandate. We didn't even barely have a board or anything like that. We just were doing what we wanted to do. And this is the main hall. It's actually a really spectacular place, but the philosophy for me was that science just is part of culture. And we're not actually, I'm just going to flick through some of the images here, the Anthony McCall show. We're not actually trying to present science through art. We're just doing science there, just like we're doing art there. We have, for instance, this is intended to hypnotize you while you're while you're here this early. This is, for instance, one of our signature series called Scientific Controversies, which I just started just on a whim, where I get two scientists together in conversation about unsolved problems, and we get to the precipice of talking about things we know nothing about. SciCon started, we had no idea if anyone would show up. We were like laying out folding chairs, and we were worried that the whole place would be empty, and like 400 people showed up to the first event. It was really stunning. Right now, we opened a list. This is Siddhartha Mukherjee, the Pulitzer Prize winner, and George Church, the biologist, in conversation. We opened a list for the one you just saw on extra dimensions, and 2 hours later, we had 950 RSVPs. And we're like, slam that list, shut, close the list. We have 200 spots, seats, and 950 RSVPs. So it just came out of nowhere, this idea that science was just a natural part of culture, has been instilled in me since forever as a scientist, but this idea that there were others who wanted to come in the same class as us and participate in this was kind of a surprise to us. This is Richard Dawkins speaking in conversation on the tyranny of socks. He opens his drawer, he grabs a sock, it matches sometimes it doesn't. Werner Herzog came and did one of our first events in the Science Studios. We are supported by Science Sandbox, a Simons Foundation initiative, and with that, we built a 3,000 square foot set of studios for the sciences. They're not laboratories, they're very much totally congruous with the rest of the building. It's a really beautiful place. This is Tuesday. I didn't realize actually when I put this in here, that's me in the corner there. This is Ronan Farrow and Gloria Steinem. We launched both of their books on Tuesday. We're just, and when I introduced Gloria, we were discussing why, as the head of sciences, are you inviting Gloria Steinem? And it was such an odd question for me. I must have had to field that question a bunch of times, but I was saying, well, there would be no female scientist if there had not been a Gloria Steinem. And this idea that our cultures are siloed is just silliness, right? I was born to a person who had a feminist awakening, which was inspired by Gloria Steinem, gave me opportunities that she didn't have, and so now I have a PhD from MIT in theoretical physics, right? That was not necessarily the life that my mother or her identical twin sister were looking at before people like Gloria Steinem. And so we're thinking about the world in a more kind of natural and holistic way. We also do author series. This is the astronaut Leland Melvin, one of the few people to have actually left the planet. Leland was spectacular and held court in our science studios, and we do a lot of those kinds of author talks now. Now we're getting approached by the biggest authors in the world to host their events. It's really confusing to us even why. Right? It really is confusing to us even why. And we do bring this to the point of thinking about astronomy. So we're doing astronomy in the gardens. This was another aspect of just doing something that came very naturally that turned out to be surprisingly important and popular to people. We had, during the Great American Eclipse, only a partial viewing from New York City. And so I really didn't think much about it. I thought we'll get 150 solar glasses and we'll put some telescopes out in the garden. The eclipse in New York City started at around 1 p.m. And we'll put some solar filters, and we just sort of announced we're going to do this, didn't really think much of it. By 9 in the morning, we had a line around the city block. I mean, this is huge. We had 4,000 people come for 150 solar glasses. And so what happened, at first, there were like a lot of tense moments. There was a lot of people running around and sweating. But then people realized you don't look at an eclipse for like 2 solid hours. And there was this sharing that started to happen amongst strangers, sharing the glasses, and then it just became this like huge community event. And I very much think about what we're doing as building a community, probably primarily, beyond anything else that we're doing. A place where people join the conversation, where they see art, where they talk about hardcore issues in science, where they break bread together. We want to build New York City's first public observatory. This is actually on top of Columbia. This is the first dome that I learned to use a telescope on. It's a beautiful old patina dome, but hardly anyone ever goes into it. It's a private observatory because Columbia University is a private university. So we want to build New York City's first public observatory. And again, people kind of ask questions that I really hadn't thought of. What are you going to do with an observatory on the top of the building? What do you mean, what are we going to do? We had 4,000 people show up for paper glasses, right? We're going to have a place where people are coming this is the building Pioneer Works, by the way. This was before Richard Dawkins' event. We had people looking at the people who wanted to look at Richard Dawkins. You know, it's very meta. And this is our thinking about how the observatory would land on the top of the building if we succeed. There have been, by the way, 250 years of failed attempts, which is really interesting. You find these old notices in newspapers about the failed attempts to build an observatory that are really quite fascinating. One of them calls for people to be interested, and at the very bottom in bold it says, ladies who are interested should contact us too. It's really cute. It's really cute, actually. It's weirdly cute. So the idea is that this observatory will be a beacon you will see from the river, and will hail people to this, what is really in some sense a community center, less glamorously phrased, and ask them to kind of focus their view on the small scale to gain a kind of astronomical perspective, right? It's kind of the small meets the large. So it's a beacon to the universe and a beacon to Pioneer Works. And somehow I'm supposed to make this a natural transition into talking about black holes. So pretend this was really smooth. So speaking of astronomy, I am an astrophysicist. It is my main area of research. And this is an example of also a collaboration between the Rubin Museum in New York City, which is an art museum, and the American Museum of Natural History. This is not a cartoon. It is actually a digital atlas or a digital map of, in this case, our Milky Way galaxy. So every object you've seen in there has been observed and is placed as cautiously as we understand its placement in the universe. Now, we can't possibly get out of the galaxy and look down. So our little observatory on the top of Pioneer Works, we're inside the galaxy. There is no leaving the galaxy and looking at it from that point of view. Here we are, third rock from the sun. This is where you are on your GPS unit. And so one of the things we think about, especially with an old-fashioned telescope or the idea of using the human eye to observe the cosmos, is how we are tied to this little rock, right? Leland Melvin is one of the few people in the world on the Earth to have left the Earth. And most of us will not leave the Earth, right? And so we're trying to understand from this perspective what the universe looks like and what's out there. And it's really quite astounding that from this location, we've been able to see 14 billion years into history and 92 billion light years across, which is the observable universe. That's the furthest reaches that light can get to us since the Big Bang. And yet everything, right? If we think about a map of, that was just our galaxy. Every object you see, and this is, again, real data, this is not a cartoon, every object you see in here is itself another galaxy. So there are as many galaxies in that observable universe as there are stars in the Milky Way. And all of that, anything anyone has ever seen or ever will see in the history of the universe, makes up less than 5% of what's out there. Okay, so everything you see is just a little kind of ashy residue left over from the Big Bang, and 95% of the universe is completely dark and invisible. And this is, of course, my favorite sector of the universe is the dark sector. And one of the intriguing objects in the dark universe is the phenomenon of the black hole. And the black hole is technically the darkest phenomena conceivable in the universe. And when black holes were first proposed to Einstein, so he writes down his theory in 1915, 1916, the general theory of relativity, where he's understanding that gravitation is really a curved space-time. And we all know those words, although it's a big leap to understanding those things. A friend of him writes him a note from the Russian front during World War I and says, oh, in the past few months, I've had the pleasure of wandering through the land of your ideas. You know, the war has been good to me, he says. And the story is that between calculating ballistic trajectories in the trenches, he's reading the Proceedings of the Prussian Academy of Sciences, you know, as you do, and he finds the black hole solution. It was not called a black hole for another 50 years, but that's what he finds. And Einstein's very impressed with this calculation, but does not believe that nature could think of a way to make such a thing. If you think of what a black hole is, it was just a thought experiment. It was just an imagining. He just said, pretend I took the sun and I crushed all the matter to a point. And he didn't ask, is that possible? I mean, after all, I can't crush this clicker, right, to nothingness. It actually resists, right? Matter resists being crushed. It's actually quite hard. And so he finds this description where such an object would have what we now call an event horizon, a region beyond which not even light can escape. A black hole is actually an empty shadow and all of these wonderful things, but nobody thought that nature would find a way to make such a thing. And this really came later during World War II, the war effort to understand nuclear physics, which was behind the technology of building a bomb. And this is one of the fascinating things about physics, is it's amoral, right? The same equations that go into understanding how to make a bomb turn out to be at the core of stars, explaining why a star shines by burning thermonuclear fuel. And eventually, and if you think that we didn't know this, you know, these seem to be facts that we take for granted, eventually stars run out of nuclear fuel, and if they're big enough, they will collapse under their own weight, explode, and the remnant that is left will be a black hole. And one of the extraordinary things about a black hole is that it's not a thing. If you were to go up to the black hole and transition through that shadow, it would be no different than stepping into the shadow of a tree. There's nothing there. There is no stuff there anymore. Whatever it was made from, whatever happened to that star, it kept falling after it carved the event horizon like an archaeological record on space-time. It kept falling and is gone. So black holes are actually empty space. It's really quite extraordinary. And so here we are now at a time when we know that black holes exist, but it surprises people that we had actually never seen one in all these years until incredibly recently. If you think of why, a black hole is a tiny thing. It's actually physically small. It's heavy, but they're physically small. If the sun were to become a black hole tomorrow, it would fit inside Central Park. Okay. And so here's this tiny shadow. How could you possibly see that against the blinding brightness of all the stars in the galaxies? There could be 1 billion black holes in the Milky Way. That's not an unreasonable assessment. And yet they're very, very hard to see. They come big, they come small. Sometimes they get bigger because they collide with other black holes and they grow. But we have only indirectly seen black holes until this century. And so, or detected black holes before this century. And so Black Hole Blues was mentioned. Black Hole Blues is about this campaign that went on, in some sense, since Einstein first wrote down his general theory of relativity. he wrote back to Schwarzschild, who was the friend who discovered mathematically the black hole. He wrote back and said, this will never happen in nature. Nature will protect us from their formation, about which he was wrong. But he said the most important thing to think about now are what we call gravitational waves, which are literally a ringing in the shape of space-time. And so let's just watch that one again. Imagine you have two black holes in orbit around each other. We think that's very common. You could not possibly see the one or the other. You will never take a picture of those. They are very small, they're very dark, they're probably very far away. But when they orbit each other, they're like mallets banging on a drum, and the whole space-time rings like a drum ringing. And there's this aspiration by people like Kip Thorne, who is your neighbor here in Pasadena, and Ray Weiss, who were the original architects of this idea, now Nobel Prize winners, that you could build a recording device to record the ringing of the drum of space-time, and that you could play it back through a conventional speaker system and listen to it. So the idea was, we will hear what we cannot see. Black holes, if they orbit each other and collide and make a bigger black hole, will ring space-time like a drum, and we could hear the ringing of the drum. And it was just an insane idea. When Ray Weiss started to build this machine when he was a young man at MIT in the late 60s and early 70s, people told him, you're going to lose your job. Like, what you're doing is not important. You're not going to get tenure. That was a big deal. You're not going to get tenure. And he's in this place called the Plywood Palace, which was thrown up on the periphery of the MIT campus during the war effort. It was supposed to be torn down, but became this place of such creativity that now many sociological texts try to understand why the Plywood Palace. So he was building this machine, and the technology of it doesn't really matter, but it was also became very important here at Caltech. It was like 1.5 meters long. And one of his colleagues came to see this machine, and the idea was like he was building like the body of an electric guitar. And if space-time was ringing, the body of this machine would record the ringing like an electric guitar works and play it through a speaker system. And they said, I'm going to just play this again. They said, you wouldn't hear it if the sun blew up. We'd do better looking out the window, right? And he says, yeah, you would do better looking out the window. And he does a 5-year study. I mean, he spends the next 50 years of his life building a machine this big, which is not 1.5 meters, but it's 4 kilometers long. Okay. It's bigger than the MIT campus. It's $1 billion. It's an insane project. Technologically, it was so challenging that it was recording modulations in the shape of space of less than 1/10,000th the width of a nucleus over the 4-kilometer span. Okay. So even if it succeeded technologically, there was no guarantee that space-time would ring loud enough for them to hear. Right, because gravity surprisingly is weak. Like the whole Earth is pulling on me right now. Look how strong I am. The whole Earth. Like if you were doing that in any other force, electromagnetism, you would be liquefied. The whole Earth can't barely have an effect on me, which is quite amazing. So gravity is weak, and so the idea of building this on 2 different coasts, and something happens cosmologically, it could be 1 billion light years away or more, and think of how sound works. It is, in fact, like a sound in space-time, how quiet it would be from here. Just think of how quiet it would be from here. So this campaign goes on for about 50 years, and it's a failure. It's called LIGO. LIGO, I'm sorry, my LIGO friends here. I know there's a couple LIGO people here. Just kidding. Here they are, some of my friends in the lab. LIGO costs about $1 billion, and by the year 2000, they finally build this. It's a very arduous campaign. It is not popular in the astronomy community. A lot of people think, why did you spend all this money on something that will never succeed? It's the year 2000, they build the machine. It's a spectacular technological achievement, and it runs for a little under 15 years, and they hear nothing. They hear nothing. And then they go up to the advanced detector. It takes them a few years. They've been building the advanced detector all the while because there was some suspicion that it might not succeed in the first generation of machines. But this is 15 years and after 50 years. Okay. Now we're up to 2015. They've installed the advanced components in the LIGO system, and it's the eve of the first science runs, and Ray Weiss, who's now in his 80s and is there all the time working on that machine. You know, he was there this weekend in 2015, and I was talking to him, and he said, if we don't detect black holes, this thing is a failure. And that's actually where the title came from, Black Hole Blues, because I was thinking, oh man, poor Ray, man, this doesn't work. Like, I mean, one other person who had been working on it for that timescale said to me, we're all just trying to stay alive, like, at this stage. So it's 2015, August. We're going into September, the first science run, and they decide they're just not ready yet. They're just not fully there. So they're interfering with the instrument this weekend. It's Sunday night, going on until Monday morning, and they're, no joke, banging on the instrument. They're doing tests like driving cars alongside it and slamming on the brakes to see if the instrument starts ringing. And middle of the night, they're tired. It's around 2 in the morning in Louisiana, where one of the machines is. The other one is on this coast. It's in Washington State. And they put their tools down. They're tired. They decide to go home. Same thing happens in Washington State. Mercifully, they've left the machine locked in observing mode. Within about a span of an hour, they're probably still on their way home from these remote sites. A signal comes from the southern sky. It washes over the machine in Louisiana. It's perfectly recorded. It skims across the continental US, where it hits the machine in Washington State. By 8:30 in the morning, Ray, who had finally gone home at his wife's insistence, is in Maine, looks at the logs. By then, this gravitational wave is billions of kilometers on, right? It kept going. And Ray says, what the hell is this? It's like, something's going on the sites. What happened was 1.3 billion years ago, and this is a numerical simulation, we couldn't possibly take a picture of it, 2 black holes collided. Very far away, 1.3 billion light years away in another galaxy, somewhere in the southern sky. Each black hole was around 30 times the mass of the sun. This is drastically slowed down. They were in the final phase of their orbits together, going nearly 70% or faster the speed of light. And they're covering about 200 kilometers orbits in fractions of a second. They collided, formed one black hole, and the ringing of space-time has been traveling to us. Think about that since like multi-celled organisms were differentiating on the Earth, right? And here they are within a span of an hour on their way home, and it strikes. This is what it sounded like. That literally was recorded, and if you go to LIGO, you can listen to the detector in the control room through speakers bought at the store. This is what it sounded like. Nope, I have no sound. What happened to my sound? I was muted. How do I turn this up? Okay. It's going to be very disappointing. Let me just warn you. When they fix this, you're going to be like, I don't know, but just imagine right now what you think 2 black holes colliding sound like, because it's not going to sound like that at all. Okay. Are we ready? Okay. So let's see. I know. It's crazy. That actually happens in 1/5 of a second, 200 milliseconds. It happens so fast your ear can't catch it, so we have to slow it down. But it happens to be in the human auditory range. So literally, if you were floating near those black holes, even in the absence of air, your eardrum, in principle, your whole ear mechanism could vibrate in response to those gravitational waves, and you would literally hear the collision in complete darkness. And if you heard that, you should really get the hell out of there, because that's like... So biggest discovery of the century, we recorded the sounds of black holes colliding. That event was the most powerful event we have ever detected since the Big Bang itself. More power came out of that collision than the power in all the stars shining in the observable universe combined. Okay? And none of it came out in light, total darkness. So this was rightfully, they were awarded the Nobel Prize. This was a remarkable discovery. Then on the heels of that come this other discovery, which was also 2 decades in the making. We see stars orbiting in the center of our galaxy, nothing. Okay? We see them orbiting and there's nothing there. So we know there's something there and it's dark. And that dark thing, we suspect, is a black hole about 4 million times the mass of the sun. It's a supermassive black hole in the center of the Milky Way galaxy. We call it Sagittarius A star because it's in the direction of the constellation Sagittarius. And it's 4 million times the mass of the sun, but it's less than 20 times the width of the sun. Okay, so we have to remember black holes are small. And there's been a campaign to take a picture of the shadow of that black hole. There's nothing there, so there's nothing to take a picture of unless there's something luminous behind it, just like how a tree's shadow works. There was also this object, which is called M87, which is a nearby galaxy, which has a black hole that's producing this enormous jet. That black hole is billions of times the mass of the sun. And so even though they're heavy, they're so small. Imagine that, just picture the sun's width, picture 20 times the mass of the sun. Now push it to 26,000 light years away, and trying to take a picture of the shadow cast by that thing is like resolving a piece of fruit on the moon. Okay. Or as they say in the experiment, it's like reading the date on a quarter from New York City if the quarter were in San Francisco. Like, the resolution is insane, and what you need is a telescope the size of the entire Earth, which of course we don't have a telescope the size of the entire Earth. This is just showing how do you see the shadow. You see the shadow if there's a backlit debris and stuff orbiting the black hole, which was not the case in the black holes that collided. They were completely bare and completely dark. In the center of these huge supermassive black holes, there's a lot of mayhem going on. They're tearing apart a lot of other stars. And so what you're seeing in the shadow is you're really seeing the shadow cast by the bright object, the bright luminosity behind it. And so this attempt to take a picture of the shadow started at least 2 decades ago. And on April 10th of this year, it was quite a day, there was an announcement of this picture. And I'm sure, has everyone seen this picture? So this was an announcement of the first picture taken by Event Horizon Telescope Project. And the way they made a telescope the size of the entire Earth is they combined telescopes and telescope arrays all over the Earth to work in concert. So that even though it was a 2-year observation, just imagine the Earth's turning, it's going around the sun, you have to keep pivoting these things, and you try to make it all feel like one snapshot taken by one eye. And so it was, again, quite a technological challenge. And the amazing thing is when they announced it, it's not the black hole at the center of our galaxy. It's actually M87, so it's a nearby galaxy. And it's the only other one that they could possibly have taken. M87 is billions of times the mass of the sun, but it's also 55 million light years away. So it's about the same size on the sky. And when I looked at this, and this brings us, this is our Pioneer X Eclipse event, back to this idea of bringing this to the community. I went out to Washington, D.C., to the National Press Club to hear this announcement because it was so important to me. What a time to be alive was the only quote I got into the New York Times. So here we are. We've just recorded the sound of dark black holes, and we've taken the first picture ever of a black hole. And we did it as an international community, and it's given to all of us for free. We will never have to pay for these things or access to these things. This is a deep scientific principle about what it means to be engaged in the practice of science and what it means to share it with the community. And when I was there at the National Press Club, we all knew what it was going to look like. So it wasn't as though we saw it and we gasped, right? We saw it, and it was more like a sense that I was looking at an image of a species, like globally, together at that moment, looking at the image of the black hole. And I was reminded that, we're all sharing these little spectacles together, and the sense especially of this reminder that that black hole is the center that we orbit. Every bit as much as the sun is the center of our solar system. That is the center of our orbit. We are in orbit around that black hole. It is not just this distance thing. It is our future. It is where all of our matter and all of our debris will end up in the very, very far future. And so I think a lot about how those stories and those feelings are things we really want to share in this practice of art meeting science. Thank you so much.